Buenos dias to everyone. I will be speaking in English, and I understand that there will be someone interpreting simultaneously, so I will try to be a little slower and clearer than I usually am. My thanks to Dr. Fernandez, to KyōDynamics Institute for this opportunity to speak to you today on the topic of building classification system for multi-hazard risk assessment. The outline of my talk is shown here. I'll spend a few moments introducing myself, my company, and the organization that sponsored this work. I'll then discuss briefly taxonomies. What are they? Their history. But I'll spend most of my time on the main topic, the GEM Building Taxonomy. We'll go to a summary and then Q&A, questions and answers. With regard to myself, here's my education and career. In a nutshell, I don't expect you to read all that, but I believe you'll have a copy of this presentation and you can look at this later if you wish. I am a structural engineer, although I'm primarily involved in infrastructure research, but I put this photograph up as just an example of one of the many kinds of structures I've analyzed. I think you may be familiar with this. It was, no longer is, unfortunately, the Arecibo Radio Observatory in Puerto Rico. And about 20 years ago, I did a dynamic analysis, structural dynamic analysis of this for earthquake loading. It was very gratifying for me to do that, by the way, because my undergraduate professor had designed the structure back in the 1960s. It's a shame what happened to it. These are some of my books and publications, but that's the introduction. My firm, SPA Risk, really SPA stands for Scawthorn Porter Associates, and it's simply myself and Professor Keith Porter. So each of us, he is a professor at the University of Colorado at Boulder, and we have one foot in academia and one foot in practice, and we enjoy, both of us, doing that. If you want to know more about the company, there's the URL for the website. I think most of you may be familiar with the global earthquake model, and I will not spend a long time discussing it or introducing it. If you don't know about it, you can quickly learn about it by going to their website, by Googling global earthquake model. GEM, the global earthquake model, was started about 15 years ago and has made tremendous progress in modeling both hazard and risk due to earthquake around the world. This is their global map, and producing many of the foundational data, such as historic seismicity, instrumental seismicity, fault parameters, building inventories, building fragility functions, and so on. And the building inventories required the taxonomy, which is what I'll be speaking about today. This is a close-up of some of their mapping of the seismic hazard in Latin America. So a taxonomy, what is it? The word was coined in 1813 by the Swiss botanist Candolle. It comes from the Greek, which simply means from taxis, meaning order, and nomos, meaning law. So it's a set of rules by which to create an order. It refers to the classification of things in an ordered system that reflects their relationships. Most famous and probably one of the first taxonomies was that developed by Linnaeus for plants and animals, which is still used today in the scientific world. Homo sapien is an example of what we are called within that taxonomy. He also had a system for minerals, by the way, but that is not widely used. An example starts from the domain and goes down through the kingdom, the phylum, and so on to the genus Canis, where we have dogs and wolves. There are many other, since that time of Linnaeus, there have been many other taxonomies that have been developed, and whatever field you work in, you're probably using a taxonomy or two right now. What I wish to speak about is a building taxonomy, which we define as describing the characteristics of an individual building or class of buildings with similar characteristics, a building typology. Have been building taxonomies in the past. One of the most common is that used, and my references here will mostly be to North American practice, since that's what I'm familiar with. This is from the US, what used to be called the UBC, or Uniform Building Code, is now called the International Building Code. And this is the taxonomy that they use for buildings in that code. Very simple and primarily driven by fire protection. This is another taxonomy that was developed in the 1970s by the state of California with regard to the state of California Department of Insurance to classify buildings from an earthquake perspective. Very simple and innovative for its time, but by the 1980s and 90s, many practitioners were dissatisfied with this. Of course, you are familiar with HAZUS, perhaps, and some of the other building classification systems that the U.S. Federal Emergency Management Agency have developed. This is the FEMA model building types that are used in all the HAZUS-related publications. And you may be familiar with this, W1 being ordinary wood frame construction, W2, and so on. But again, this is very unsatisfactory. For example, the last item in the list, URM, or unreinforced masonry bearing wall buildings. There are so many different kinds of unreinforced masonry bearing wall buildings that to all label them with a common label is just not accurate or useful. And so it's very unsatisfying. And that's what drove the development by GEM to develop this. And this is a screenshot of some of the from the report that I'll refer to later that supports this work. We wrote a 150-page report on this. I'll talk more about that later. But I just wanted to say that with regard to the history of it, there's more in the report. This shows you how we discuss how taxonomies from the insurance industry, the construction industry, and so on. I'm not going to go into that any further now. Rather, let me just say that in doing this, we reviewed all of this, and we came to the conclusion that a building taxonomy useful for risk analysis, particularly earthquake risk analysis, did not exist when we were doing this work. So the Global Earthquake Model funded this project, and the purpose was to collect information on buildings around the world to develop a basis for assessing their seismic vulnerability and associated risk. The taxonomy, at the beginning, we set ourselves certain objectives. It should be international, cover all parts of the world, and be able to be applied in any part of the world. It should meet the needs of users who are able to collect information in sufficient detail, but also others who have access to only very limited information. So it should be both at the same time deep where that's possible and where it's not, to be relatively broad and shallow. On the other hand, also, we set an objective that should be manageable, and there should be a balance between the depth and the breadth of coverage. Vision, therefore, was to create a unique record or code for a building, or for each building, something like a genetic code or a genome. In other words, a building genome. This approach is in line with other technologies that have been emerging over the last few decades, such as the Building Information Modeling approach, or BIM, and recent taxonomies that have been developed for the construction industry, such as OmniClass, and also, by the way, for the insurance industry. So our idea was, just as each of us has a unique DNA, each building has a unique DNA, so to speak, and that DNA is a combination of the location of the building, its cladding, its basic structural systems, the materials of construction, the lateral force resisting system, the height when it was built, the occupancy, and so on and so forth. And just as the human genome is very complex, if we're going to accurately develop a taxonomy for buildings, it's going to become rather complex. But that complexity actually can be captured by modern IT for application in things as simple as a barcode or in this case, a QR code. So while the complexity may be daunting, modern IT allows us to use all of this detail if we can develop a taxonomy to support it. So that's where we went. So we decided that the taxonomy would be a combination of the different attributes I just mentioned. Each of the attributes would correspond to a specific building characteristic. We have to clearly define the attributes, and we have to develop a set of values for that attribute. And as I mentioned earlier, we would have a basic taxonomy. I'm referring now to the right portion of the figure here. We would have a basic taxonomy that might be captured very quickly by remote sensing or street surveys, that sort of thing, or even from just a desktop study using existing censuses and databases and literature, but also a detailed text. The system should be able to support that, but also should be able to support a detailed taxonomy where relatively knowledgeable engineers will be able to accurately provide much more data from the drawings or from a survey of the actual building or from the building information model. So the initial list of attributes we came up with are shown here. There were 13 of them. The direction of the lateral force resisting system, in other words, the orientation of the building, so to speak, the material of the lateral load resisting system, what type of lateral load resisting system it had. Was it a braced frame or a moment resisting frame or shear wall or whatever? The height of the building, and we define how to measure the height. The date of construction or the date of retrofit. A building built 100 years ago but retrofitted 10 years ago is not a 100-year-old building from a earthquake point of view. The occupancy, residential, commercial, and so on. The building position within the block, I'll talk more about that in a moment. The shape of the building plan, the structural irregularity, the exterior walls, the roof, the floor, the foundation system, and so on. Now, I have a little video here that actually goes through this in a bit more detail. This was put together by the project, and let me just show it here. It goes on for 3 or 4 minutes. And let's see here. You may not be able to hear the audio. I'm sorry, I beg your pardon. This doesn't seem to be running here. Let's see. I'm sorry, the audio is Alejandra, is the audio coming through?
No.
Okay. Well, we'll skip the video then. The video was basically it was actually produced for lay people to very quickly lay out more or less what I just said. It was going to repeat some of what I just said and what I'll say here. These show those 13 attributes again, and for each one of them, you can see that we actually they are the primary layer, but then beneath them, there are further attributes. For example, if we look at the height, we define the height as the number of stories below ground, the height of the ground floor above grade, and the slope of the ground. And then, of course, the height of the roof above the ground also. The height of the ground floor above grade, by the way, may not be so relevant for earthquake concerns, but we were also looking ahead, and that would be of great interest for flood-related risk. But this was the first version of this was focused on earthquake, but still we were trying to capture some of these things. So yeah, I hope you've had a chance to look at this diagram here. I'm not going to go through it in detail. And then if we look here, for example, if we just take a masonry building, as I mentioned before, masonry is construction exists around the world in many different forms, depending upon the local materials and other things. So this shows you an example of the material technology just for masonry. You can see the different kinds of masonry materials we have here. Masonry units that are unknown, or perhaps adobe block, or stone of an unknown technology, or rubble, meaning field stone or semi-dressed stone, or dressed stone, or fired clay units, but we don't know what type, or fired clay solid bricks, or fired clay hollow bricks, and so on and so forth. So all of these different kinds of masonry units can be defined within the taxonomy. We have codes for each of these. Similarly, for the material the mortar, for example, was there no mortar? There are examples, in various places there is masonry that's built without any mortar at all, so-called dry masonry or dry stone. Then there's mud mortar, there's lime mortar, there's cement mortar, and so on. And the different kinds of stone. Is it limestone, sandstone, granite, and so on, or unknown? And the reinforcement. Is steel reinforced, wood reinforced, bamboo, cane, or rope reinforced? In parts of Latin America, there's a type of construction called bajareque, which is reinforced with cane. Some of you may know much more about it than I do, and so on. So all of these different attributes are examples of the kind of detail we go through in the taxonomy. All of these attributes were then compiled in a series of tables. Each table contains the values for one building attribute. This is, for example, the table for the lateral force resisting system. And you can see that we have at level 1, we have a lateral force resisting system, and it's L99 is a code for meaning it's an unknown lateral force resisting system. LN means there's no lateral force resisting system. LFM means a moment frame. LFINF, an infield frame, then a braced frame, post and beam, and so on and so forth. And then over on the right at level 2, depending on whichever lateral force resisting system it is, there's a code for defining it as ductile, non-ductile, or equipped with energy dissipation devices. Level 1 and level 2. Now, all these different things I've been talking about need to be more precisely defined. So a significant part of the project was developing a glossary for the GEM taxonomy. We're going to define terms. We're going to use terms, but we need to define them. And this is on the GEM website. You can see it's alphabetically arranged. This is for the entry for masonry. And actually, by clicking on that, I'm hoping it will take us to the GEM that page. I don't see it happening. Again, sorry about that. My connections today are slow or don't exist. But the idea, if you, again, this is easy to find. You can just look up GEM glossary, and we define each of these terms. And similarly, putting all these terms together can become very daunting. So we developed a GEM building taxonomy tool, or called TaxT, and it goes through and you enter whatever you know about it. And again, I'm going to try to go to that. Now, I guess because of the Zoom, my internet is slow. You can go through and enter all these items, and it will then develop in the end a code like this. So here's an example for a reinforced concrete structure cast in place with infield frames in one direction and a different kind of lateral force resisting system in another. The building has a rectangular shape. It is detached from other structures. That is, it is not close to other structures, and it's a heavy industrial. So all of those aspects are covered in this code here. And I used to be able to read this code off very easily. I can't right now. Here's another one, a 14-story residential reinforced concrete building. So you would enter all the information you need, and the tax-T tool that I showed you would just generate this code. And this code is what goes into a database. Here's a third one. And this is a single-story post and beam bamboo house. As you can see, it's what's called vernacular, or relatively non-engineered construction from, I think in this case, Southeast Asia. So you can see the taxonomy was designed and is constructed so that we can go from heavy industrial buildings to more ordinary urban type buildings that we see to rural buildings in any part of the world. And all of this is possible. The taxonomy can describe any of these kinds of buildings. Let me give you a couple more examples. These are examples that were generated by contributed by some people in Iran. This is a confined masonry building in Iran. Now, all of this, I know you cannot read all that data, but all of those, every one of those fields is a piece of information that gets entered into the taxonomy if you wish, if you're able to have all this information. You fill out as much as you can. Where you don't know the information or you're not able to acquire it, you just leave it blank, and the taxonomy, the code winds up being longer or shorter based on that. So this is the taxonomic code for that kind of construction. Similarly, same people developed, give another example, again from Iran, a high-rise building, and this was the taxonomic code for that high-rise building. So you can see that with a string of basically one line, you're able to describe a tremendous amount of information about a building that can then be used for regional earthquake damage loss estimation. And when I say regional, it can be at a very broad scale, say nationally, or it can be at a relatively small scale within one neighborhood or so on. Now, so that's a description of the, whoops, sorry. I'm not sure what happened there either. Let me back here, sorry. That's the description of the taxonomy. We then developed a first version, and then it was tested. The evaluation and testing was performed by the Earthquake Engineering Research Institute. Many of you may be familiar with EERI, and also the International Association of Earthquake Engineering World Housing Encyclopedia Network, and so on. It was led by Marjorie Green, who's on the right there, and these students here, they wrote that video and they did the testing. The testing was done through via the World Housing Encyclopedia. There was a website. We had about 116 reports that were generated, like the one I showed you for Iran. You can see 16 from North America and so on. This was the distribution, and this shows, again, about half of them came from Asia, South America, 9, and so on. This was, again, another example of a taxonomic string for this relatively simple building. And again, as I pointed out earlier with the QR code, with a handheld with the tax-T, which is on a telephone, a smartphone, you can go basically to the building, inspect it, record as much information as you can, and then it will generate this code. Or if you're not able to do a field survey, you can do the same thing from whatever information you have on the desktop. So this tool, then the inventory capture tool, captures the location. This is on a smartphone. You can, using Google Maps, you're able to see where you are physically. So you can see the irregularities, the plan irregularities of the building, and so on. The tool for each item, each attribute that you want to enter, if you're not sure, the entire glossary is in the phone, so you can just click on it, and it will bring up and help you to make a decision as to whether it's an infield frame or a shear wall, and so on and so forth. So the applications are meant to be global. So this was released, and there's a report. It was finished about 2013. Since then, the global earthquake model has gone on to extend it to multi-hazards. And as I mentioned earlier, this was the vision from the beginning, that it wouldn't only be earthquake, and they're extending many of these attributes. They're adding attributes and further extending them to try and make this also applicable to high wind hazard and flood hazard and other hazards. Still, they're only scratching the surface there. They haven't gotten too far in that, but that's the vision and direction. And these are some of the codes. The version 2.0 was the version finished in 2013, and the codes are shown on the left. The codes have been the new work is called GED for all. It's a global exposure database for all, and the form of the taxonomy has changed a little bit, not too much though, and that shows it on the right. Now, the taxonomy has been used to acquire or to develop building inventories in several parts of the world by the GEM Foundation and by others. There's a paper that I'll mention, that I'll provide you links to at the end, which discusses this in much more detail. But GEM was funded by the EU to develop a inventory of reinforced concrete buildings in Europe, with taking into account trying to capture whether they were designed by a seismic code, and whether the code was a so-called low code, moderate code, and so on. This is from a paper by Crowley and Despotaki in 2021, and the taxonomy was used in developing this. I'm going to close here with just a few remarks. The taxonomy was developed. The work we did was considered a initial step. It was designed to be adaptable as more knowledge and techniques and research become available. And as you can see already, has gone from the original version 2.0. Of course, there was a 1.0 also, but from the stable 2.0 to a third version, GED for all. But going forward, there's many things that need and could be done. For example, first of all, it needs to be more broadly disseminated and used so that it becomes a global standard. So this talk is one effort in that direction. On a lot of the publications that I've referred to and that I'll mention again at the end are also efforts in that regard. But as each of you are doing work in your region, if you might look at this as a useful tool for describing the buildings. Not only will you be contributing to a global database, but you will be also gaining from all the work that's gone into this. And there are fragility functions that are now available for many of these standard buildings that are described by standardized taxonomy and so on. So we're trying to go to a global standard here. There are many improvements that can be made to the taxonomy. We never dreamed that what we did was perfect, far from it. There are many more attributes that could be captured, not only more attributes for earthquake, but also for multi-hazards. We can start trying to extend it to capture attributes that are relevant for climate change, for energy efficiency, for occupant health, and there's many other applications. It's ironic, isn't it, that buildings are one of the oldest things humans have ever constructed. I mean, humans have been constructing buildings from prehistoric times, and yet we don't have a clear, simple way of defining them. That's what this taxonomy tries to do. Another whole direction that can be pursued by researchers is integrating this with other aspects of IT applications in the built environment, such as taking information off of a building information model, the BIM, and being able to just download, just write a piece of software that takes the BIM description and converts it into the taxonomic description. That would be very useful. That would be a good master's or PhD project for students, if there are any professors listening. Another one is artificial intelligence, or AI, automated cataloging of existing buildings using Google Streets or other types of imagery. And of course, there's been a lot of work done in this regard. Some of it, by the way, at the University of California at Berkeley by Professor Khalid Mosalem, but in other locations also. But this is another area that could use still much more work. And I'd be very interested in hearing, these are only a few ideas. I'm sure the audience has many more ideas. So in the Q&A, I'd be happy to hear what your ideas are on that topic. So lastly, I'll just mention with regard, whoops, sorry, let me, I'm not in control of my PowerPoint as well as I usually am. Pardon me for that. I'll just mention here, in terms of resources, if you go to the GEM webpage, there's a screenshot on the left. There are many publications on the webpage that you can download that are all about the taxonomy or the applications, such as the European one I mentioned, and there are others. It's also been used, by the way, to do a broad risk assessment for South America by GEM, very broad. The center image is the version 2.0 report that we produced back in 2013. Professor Svetlana Brzev was the primary author. I was the co-PI, and there are other people there. That report is one of the publications you can download, and is still the definitive report on this whole topic. The GED for All project that I mentioned, sort of version 3.0, is documented in a paper that just came out this year. The primary author is Vitor Silva, is shown on the right. And any of you see the DOI reference for each of these papers at the bottom there. And this paper describes some of the applications like the European model and so on. I might mention that Vitor Silva, the primary author of the paper on the right, is a GEM employee and has really taken the lead after Svetlana and I moved this to a certain level and handed it off to Vitor, and he's been taking the lead since then. And I encourage any of you to contact him, as well as, of course, myself, if you have any questions or anything. And he's in Pavia, Italy, at the GEM Foundation. So I just mentioned the taxonomic team. For the original work, the co-PIs were Professor Brzev and myself. She was at British Columbia Institute of Technology. She's now moved to Serbia. She's located in Serbia now. And some of you may know Svetlana. She's a leading structural engineer. Other people that contributed to it was Professor Charlson of Victoria University at Wellington, New Zealand, Vitor Silva, I've mentioned already, Luke Allen, Keio Jaiswal, and Marjorie Green. So with that, I'll say thank you, muchas gracias, obrigado,